This is an AP style question that was shared by Mr. Richard White of LearnAPPhysics.com, and I thought I would share it with you guys because we kind of got interrupted when we were discussing angular momentum and other angular quantities. So I thought this would be a good chance to review some of that. So we have a solid disk with this radius, with this mass, with this moment of inertia, and it rolls along a surface without slipping at a constant velocity of v. What is the angular momentum of the disk? All right, so angular momentum, uh, we want to remember here that all um, angular quantities have are related to a linear quantity. So if we go back in the Wayback Machine and remember that linear momentum or translational momentum depends on the inertia of the object and the velocity of the object. And then if we apply this to angular momentum, yes, I know that can get confusing, but angular momentum, it depends on both. So let's see. In translational momentum, mass is a measure of the inertia of an object. How does that apply to rotational situations? Well, the inertia of the rotational inertia of the object. It depends on the motion of the object. How does that apply in rotational situations? We have an object moving rotationally with an angular velocity. All right. So that's angular momentum, is the motion of that inertia, rotationally speaking. All right. So now that I've done all that, I can apply some of the information I'm given. Well, here I'm told, if you recall, each shape has a different rotational inertia associated with it based on where the mass is distributed in that shape. For a solid disk, that inertia just happens to be, that relationship just happens to be 1/2 the mass of the object times the radius squared, i.e. the radius of that circular object. All right, so if we substitute in here, the angular momentum would equal, let's pop that into there, 1/2 m r squared omega. All right, so if I stop there, I take a look over at my answer choices, and let's see, the only two I see that have an omega in them are this one and this one, but neither of them matches what I have. So now it looks like I've got to try to somehow get a translational velocity in there. Well, this is where we have to go back in the Wayback Machine. If you remember before we went on break, we were talking about the relationship between linear measurements and angular measurements. Well, the relationship between linear velocity and angular velocity is this one. They are related uh, by the radius of that object. So if we do some rearranging here, let's solve for that. Equals velocity over the radius, and I guess to stay consistent here, the radius of this object is capital R. And now I take that relationship and I plug it into there. All right, so let me switch colors here because this is starting to get a little bit muddled here. So let's rewrite this. So there's my angular momentum is equal to 1/2 times m times r squared times velocity v over radius r. And when I do that, I see I can do some simplification there. So the angular momentum is equal to 1/2, since that cancels out, m r v. All right, so now I go back and I take a look at my answer choices, and it's not that because I've got that in front of it. It's not that. The answer must be B. All right, just a quick reminder of what we mean, what we're dealing with angular momentum and substituting some of those values around.